Good evening, everyone. I am Bharat Suthar. I'm an associate professor in the Chemical Engineering Department. So on behalf of the Institute Colloquium Committee as well as Department of Chemical Engineering, it is my pleasure to welcome you all for today's Institute lecture at IIT Bombay. What I would like to request is that if you have a phone, can you put your phone in a silent mode for the duration of this talk? That would be much appreciated. And we are delighted to host this lecture on the topic that lies at the intersection of polymer physics, electrochemistry, and rechargeable battery technology. This is an area which has a huge fundamental and scientific importance, as well as very strong technological relevance. It is my privilege to introduce Professor Nitash P. Balsara, Charles W. Tobias Professor in the electrochemistry at the University of California, Berkeley. He also has a joint appointment at Lawrence Berkeley National Lab. Professor Balsara is internationally recognized for his pioneering contribution at the interface of polymer physics, electrochemistry, and energy storage. He got his bachelor's degree from IIT Kanpur, followed by master's degree from Clarkson University, PhD from RPI, and subsequently he had postdoctoral positions at the University of Minnesota as well as Exxon Research and Engineering Company. Over the past 3 decades, his work has fundamentally shaped our understanding of polymer electrolytes, ions, and solvent transport, as well as electrochemical phenomena relevant to batteries. His research bridges fundamental science and real-world impact. He co-founded 2 battery startups, CO, which has been acquired by Bosch, and Blue Current. Professor Balsara's contribution has been recognized through numerous prestigious honors. The list is long. I would just take one name. He has received Polymer Physics Prize of the American Physical Society. He's also a distinguished alumnus from IIT Kanpur. Today he is going to speak on the title or the topic of movement of polymer molecules under electric fields and relevance to rechargeable battery. With that, it is my great honor and pleasure to invite Professor Nitash Balsara to deliver Institute lecture. Please join me in warmly welcoming him.
Yeah, thank you all for coming on this late hour. The fact that you could find your motivation to come here rather than do something else in the evening is very much something that I'm grateful for. I've had a great day, a great 2 days actually. I've met many friends, made new ones. But I particularly appreciate the chance of talking to the students. So I think that was, in my view, a highlight. I think they represent the future, and they represent the future hopefully better than I did when I was a student. I'm going to talk about the subject that Bharat told you about. I have to also say that I have really felt welcome because of the all Priya, Bharat, Chandra, all of you who have made this possible, and so I feel just feel happy. So I'm going to tell you about the movement of neutral molecules under electric fields. And the list of experimenters on the first line are my students, and I'll go through their contributions as I go along. The folks in blue are folks at Oak Ridge National Lab. Chris Takis is at Stanford, and then a list of senior faculty at Berkeley. John Newman is really my mentor, and there are theorists that I will talk about who Chao Fang is now a faculty member in Hong Kong, and Rui Wong is an assistant professor at Berkeley literally changed my life. The talk is organized as follows. I will first talk about polymer electrolytes and batteries and ion transport. But before I start, I want to put a disclaimer that the work is relevant to solid-state batteries, and I am the co-founder of a battery startup in that space called Blue Current. And this is a managed conflict of interest, managed by Lawrence Berkeley Lab, Department of Energy, et cetera. The talk has very little to do with technology. I'm happy to talk about startups and things like that, but it's basically not what I will talk about, okay? Just to make sure you get the subject. So coming back, I'm going to introduce why polymer electrolytes, okay? So you all carry a device in your pocket, and perhaps all of you know that 1/3 of that device is a gasoline-like liquid. Okay? The device is mostly a battery. The battery contains 2 electrodes and a liquid electrolyte that conducts ions from one electrode to the other. It works beautifully, but here is and you find lots of announcements. In fact, I was told about an announcement by Mahesh today about how some battery has blown apart every other battery. And the truth is that in most metrics, commercially, not much has happened in the lithium-ion battery escape. I mean, given all the investment and research, this is almost an absurd plot. So you start out at, I'm looking at one parameter, energy density, and this is something that everyone cares about. So you want to start a startup, the first thing they'll ask you is, what is the energy density? It started at 200 watt-hours per liter, and at about 2012, it reached 730 and then stopped increasing. Okay. At any given year, people make a whole range of batteries, and that's the nice thing about having a peer-reviewed publication. But the top has not changed much in the last 10 years. And so there's a feeling that perhaps there are some other chemistries that might take this number to a higher value. And in my mind, the highest possible value is 1,000 practical. Okay, that's what roughly the periodic table allows us, and the question is, can we ever get there? And it should be clear that this is not going to get to 1,000 anytime soon if we just continue along that path. The energy density of a battery is constrained by electrodes, which in your case are graphite and transition metal oxides. And I'm going to just shut this door. And one approach to enabling other electrodes is by using a solid polymer electrolyte. Okay? And so that's the motivation for me to study the polymer electrolyte. I will show you no data on batteries themselves, but I'm just interested in how ions flow through a polymer. So this is a picture of the battery that you all carry. If you look, you will see an electrode. First of all, you have 2 electrodes with particles and an electrolyte that floods the distance between the 2 electrodes. The electrolyte is a mixture of a salt inside a liquid, and initially, when the battery is not being used, you have some concentration like C average. And now you want to pass current through the battery. So lithium ions actually come in from the left and get out from the right. And we have known for a long time that this creates gradients of salt concentration. You get more lithium ions on the left, less lithium ions on the right. And if you keep increasing the current, the magnitude of the gradients increase. And at some point, there is a region where there is no ions. So if you charge the battery at current I2 fast, then you will get half the capacity at I1 because half the battery is inactive. At some point, the entire battery is inactive, so you can't charge your cell phone in 5 minutes, because if you try to do that, you would get zero capacity. Okay? Your gradients are too slow. So concentration gradients are, in my view, the most important aspect of what is happening inside a battery. And this will be the development of the story. What are the factors that control it, and how do we get on top of it? So here's a picture of a polymer electrolyte with two symmetric electrodes, plates of lithium. And because I connect it to a potentiostat, I get lithium coming in from one side and going out the other. This voltage, when I switch up the current, is 0. It's a very nice, simple system that allows you to focus on the electrolyte. And you think of this as a race course. The positive ions, lithium, will move to the negative electrode. The negative ions will rush to the positive electrode. And when you have planar electrodes, the race course is well defined. It has a well-defined length, and that's why I like planar electrodes for fundamental studies. This is the very classic picture of how ions move, at least in the beginning, in a battery. Okay? Now, the design of this polymer, or the solvent in your case, has to be very delicate. It must encourage lithium ions to come in, but when you can't be too encouraging. Otherwise, the lithium ion will just stay in the battery. You want it to go out the electrode. So it's like a guest. You want them to come for maybe 2 or 3 days, but you don't want them to come for 3 months. Okay? So it's not so easy to describe exactly what the electrolyte actually needs to be. So I'm going to tell you about two polymers. Chemical structures are shown here. This is the salt, like sodium chloride, except it's the negative ion. And I will talk about different salt concentrations, and I always use the term R, which is a ratio of moles of lithiums to moles of oxygens. You see, this has only one type of oxygen. This has many types of oxygen. I'm just going to count all of them. And that's, we can of course convert it to molarity or molality. And whether or not I can use this polymer in the application depends on how much current it can support. So the question is, how do you measure that current? Well, in this symmetric cell, it's very easy. Okay? You apply a current, and the voltage goes up and saturates, and then you see some funny business at 0.9, which you will ignore. And then at 1.1, the voltage goes to infinity. And all of us sort of protect our batteries, and we stop the current. We stop when the voltage reaches some sort of cutoff. So there's a clear divergence between this current density and that current density. And I would say that the critical current, or the limiting current, sorry, is 1 in this case, 1 milliamp per centimeter squared. Okay? How do you think about why is the voltage going to infinity? Well, the concentration, if it approaches 0, virtually everyone has used the Nernst equation to calculate potential. So if you use the Nernst equation, log of 0 is minus infinity. Okay? So the divergence of a voltage is a signature that the concentration at some electrode has gone to 0. Simple, okay, simplest answer. And so these experiments are actually pretty tricky. And the ones that I'm going to show you were done by Zach and Jay Young. And here is this limiting current, which was 1, for the two polymers, PPM, that funny-looking polymer, and PEO, which is actually the standard, and as a function of salt concentration. So the first point is that the limiting current goes up, and then because of frictional effect, it goes down. And if you look at PPM, it goes up and down, but the peak is about a factor of 2 larger than PEO. Okay. So I claim that the best polymer electrolyte in the world is PPM, this polymer that somehow I was involved with in some capacity. Okay. It also happens to this peak. So many of you must have heard of conductivity of the electrolyte. These peaks are not at the conductivity peak of the electrolyte, because there's a lot of other things that happen. And so The limiting current, in my view, in my view, the most important metric of any electrolyte. Okay. So that's my introduction. The next thing I want to talk about is subdiffusive motion. So this is a picture of the liquids you carry in your pockets. You have salt, you have ions that are dissociated, and typically each cation, the lithium ion, is surrounded by some number of solvent molecules, usually about 6, 8, something like that. And all of these things are diffusing everywhere. So if you talk about the mean square displacement, you put somehow you color this and then find how far it has moved. In the long time limit, the mean square displacement will go linearly with time. Okay? But on very, very short time scales, the solvent molecules, for example, will feel the friction with the positive ion, and it will move at a slower, it'll move with a lower slope. And this lower slope is what one refers to as the subdiffusive motion. And roughly spoken, this transition from subdiffusive to diffusive, this time scale is roughly the time scale that this solvent molecule hangs around the ion. And you can imagine that this is a very important time scale, because the solvent ion, in order to move across the electrolyte, has to escape from that cage. In 1993, it's hard to believe, but in 1993, we got the first estimate of what that time constant might be. And in the case of aqueous systems, it is 1 picosecond. Okay, this is a paper by Graham Fleming, a professor at Chicago at that time. Beautiful 2D IR experiments that I don't understand, but if you look at this time scale, it is 1 picosecond, and the decay of the structure factor on that time scale roughly tells you that this water molecule hangs around the ion for about 1 picosecond. Fast forward to 2016, one of his students, he thinks he's one of his best students, Min-Hei Cho, in Nature Com, said that in the liquids you carry in your bucket, that the time constant is about 1 picosecond, based on the same technique, 2D IR. Okay? And if you think about it, it actually makes sense. You know, if you take aqueous solutions, you shake them around, you get a certain viscosity. If you take the battery liquid, you take it out, it looks like the same viscosity. Except, this paper came out a few years later in JACS, and the main point of this paper is that that paper is completely wrong. Okay? It's wonderful. They don't give you the right answer, but they tell you that that paper is wrong. You can see, for example, they say that ultra-fast 2D IR can probe exchanges. However, in the absence of solvent exchange, you get the same signatures, hiding the desired process. And we estimate that no exchange takes place for at least 100 picoseconds. So in the liquids that we have been carrying in our pockets, until 2022, it wasn't known if it was 1 picosecond or 100 picoseconds. Okay. And to me, what's also interesting, of course, is another power of simulations. Everyone does simulations and get whatever answer they want. So the first group had got 1 picosecond. This group got more than 100 picoseconds, like 500. Okay? Don't ask me to ask why they got different answers. This is just a fact. You can read the papers. So we thought that we thought about what we might do to measure solvation dynamics on smaller timescales. And the technique we came up with is quasi-elastic neutron scattering, and my student Neil Shah is the one who did this experiment. A neutron beam comes, hits the sample. It has a well-defined peak energy with well-defined energies, and when the energy spreads, it is because of the exchange of energy between the neutron and these objects that are moving inside the sample. I mean, this experiment requires a nuclear reactor at one side. The experimental chamber is about the size of this building, this room. And there in the middle is a little polymer sample with detectors all around, much like that, actually, like those little squares. Very imposing experiment. But it turns out that neutrons are only sensitive to hydrogen, because hydrogen atoms don't have a neutron. All other atoms have neutrons. And so when a neutron sees a lot of stuff, this quasi-elastic signal is completely telling you only about the motion of hydrogen. And in our polymer electrolytes, the salt doesn't have any hydrogen. You can go back and check. All the hydrogens are on the polymer. So we are looking at the motion of polymer chains and how it is affected by the presence of ions. And in polymers, this subdiffusive regime is known to have a power law of a half. So we expect the mean square displacement in subdiffusive region to go as t to the half power, not t to the 1 power. And so instead of making these kinds of plots, I'm going to show you for convenience, I'm going to divide by t to the half so that when I get this subdiffusive motion, it's a plateau. And you don't have to try and determine scales by looking at slopes. Okay? It just makes it simple. And here are the data in the next slide for these two polymers, polyethylene oxide, or PEO, or polypentyl malonate, which is PPM. And again, this is the salt concentration. R squared divided by t to the half versus time. Okay? In PEO, you get beautiful plateaus. The plateau value tells you that adding salt from 0 to some value of 0.2, the mean square displacement has gone down for the same time. And this is because when you add salt, you get more friction because those ions are sort of sticking to the oxygen. When you go to ppm, a very strange thing is seen. You see a plateau, but at the highest salt concentration, this goes as a slower power than t to the half, then settles down, and then becomes something else. So this trough is something that we thought about for a little bit. Why is this happening? And that's when we turned to simulations. Rui Wong joined our department, and as I said, he changed our life. Until then, we had no molecular pictures. So these are typical snapshots of the two polymers. The snapshot of PEO is in the literature. Okay, what happens is if you have a lithium ion, which is this blue thing, you can define its neighborhood like the circle, and these red oxygens, you can see about 6 of them in the neighborhood of this ion, but all of them are donated by one chain. And this is well known in polyethylene oxide. It's a beautiful structure. It has the exact spacing of a crown ether, which is known to solubilize cations, like lithium. What was news is that when you look at this polypentyl malonate, the oxygens, only these carbonyl oxygens interact with lithium. Okay, that turns out from simulation. And you need at least 2 chains to be interacting with this lithium. So in PEO, you have 1 chain. In PPM, you have 2 or 3. Well, this is one way to look at it. These are probabilistic plots, because this is a liquid. And what you see is that typically the anion is far away from the lithium, and you have about usually 1 chain and 0 anions. So this peak at 1 and 0 tells you that the typical solvation shell has 1 PEO chain and 0 anions. Of course, you have all kinds of other structures because they are all moving. And so the lithium ion is slowed down. The hydrogens are slowing, the lithium ions cause the slowing down of these solvating chains. Okay, that's the idea. And the picture I have is this way. Okay? In this case, as I said, you have a peak at 2, you have a peak at 3 chains, and many more anions interacting. Much more complex and somewhat ugly sort of, the pyramid is nice and simple. This is very ugly. It looks like a cockroach or something. But this picture suggests that the anion, the cation is at least connected to 2 chains. And this is to me, very interesting, because that means the ion is making temporary crosslinks. And those of you who work in polymer science will know that there's a huge literature on temporary crosslinks, hydrogels, and things like that, where the crosslinks come and dissipate. And so this is a connection between polymer physics and electrochemistry. We just said that because of this picture, the solvation time, which was previously determined by 2D IR, can be determined if we just see how long the network survives. And in the polymer physics literature, it was known that this mean square displacement over t to the half would have this signature in reversibly crosslink systems. And so we went to the simulation. This is Xiaofang, and then we get the same thing that we saw experimentally. And from the simulations, we can tell that, in fact, the lithium, the solvation lifetime in our system is 500 picoseconds. And this is the first measure of solvation time that is not 1 picosecond, and we think it's correct. The importance of solvation time is really something that is easy to draw in pictures, and that's what I'll show you. There's some potential, there's some potential plus phi on one electrode, and we call it 0 on the right electrode all the time. You're allowed to do that. But you see, when the solvation time is large, as this lithium is moving, it's dragging the solvent with it. Okay? And then at some point, you get a fluctuation. The lithium ion hops and goes there. And we can see that in our simulations, and I'm drawing this picture because it just makes life a little easier. On the other hand, if you have more than one chain, then the two chains are independent, and it drags a lot less solvent. Okay? And that is our hypothesis for why ppm is better than PEO. It's better because the neutral molecule is moving less. It's a hypothesis. I want to go and talk a little bit about continuum scales, because we are not interested in some 1 angstrom. I mean, I should tell you, I should when I talk about these, it's important to note the value of this x-axis, which I refuse. The x-axis is nanoseconds. The y-axis is 1 angstrom square per nanosecond to the half power. Okay? You're looking at angstrom level motion in the Quenz experiment. And of course, because solvation is very local, that's arguably the right length scale. So I'm interested now in millimeters, right? I want to know how this all translates as you go into batteries. And if you want to go to the simplest picture, you would say, well, I have a potential. In fact, if your potential is some phi at one point and 0 at the other, usually you will draw a straight line, and that would be valid at t equals 0 for technical reasons. Then these ions would start moving and mess around with the straight line, but the difference will be the same. Okay? And these velocities, at least initially, are given by the charge times the mobility times the gradient of the potential. And this gradient is constant, so all these things will be moving at one velocity. Z is the charge. When it is plus 1, the velocity will move in the positive x direction because the gradient is negative. Okay? So that's how I've arranged the equations, and the anion moves in the other direction. Since the solvent has 0 charge, and if you use this formula, you'll get 0 velocity. Here is an example of a paper written not so long ago on the general behavior of ions. And in this paper, they talk about how these how things move under an electric field. And the flux of the crux of this paper is that if this ion is, let's say, moving here and leaves a void, then 3 negative charges must move there because that's the volume constraint. The solvent is not even in the picture. Okay? They just assume positive and negative charges are moving. And this is true of the entire literature prior to 2012. 24, in lithium ion, the motion of the solvent has been ignored, and with good reason, perhaps. So if you take a polymer electrolyte, initially the ions are all at uniform, and you apply an electric field, and you get this picture, right? The ions get concentrated at one side. And for this to happen, polymers from here have to move there. Okay? There's no way for this concentration gradient to occur without polymer motion. So how do you describe this motion is what I started to think about. And I went to my mentor, John Newman, and said, all right, in your book, you have this wonderful equation for the development of concentration gradients in electric fields that many people in this institution also use, by the way. But this is the equation from the textbook. C is the salt concentration. V0 is the velocity of the solvent, diffusion coefficient. So this is standard accumulation. For those of you who are chemical engineers, you draw a little box. You say how much salt is accumulated in this little volume. That's dc dt. That's your control volume. That term is, if the solvent is moving and it carries the ions, then you would get the gradient of that as one of the things. What's coming in must go out. This is diffusion, okay, corrected for activity coefficients, but this is basically diffusive flux. And the only thing that matters as far as the electrical part is this term, which is the dot product of the current times the gradient of a parameter that I'm going to tell you all about, called the transference number, T plus 0. Okay. So here is the equation. Now when everyone uses this equation, they say, well, the solvent can't move, so we set that to 0. They also assume that the transference number is independent of concentration. So that gradient, no matter, you have a concentration gradient, but you don't have a transference number gradient, so that is 0. And then you're left with simple diffusion, and you solve, and you get answers that are in some classic papers like this one. Right? This is a paper that is cited, the only theory paper cited in the lithium-ion battery Nobel Prize report is this paper. Okay. But, you know, this thing has two variables that can depend on space and time, the solvent velocity and the concentration. And so you need two equations. This is sort of obvious. And I asked Newman, you know, what is that equation? He said, I don't know, but I can't solve everything for you. So luckily for me, I had time to think about this during COVID. COVID doesn't happen, this talk doesn't happen either, by the way, because I got to think carefully about what was in my, this missing equation is the continuity equation. And many of you who are chemical engineers might recognize this del dot V equals 0 is the continuity equation that you use in fluid mechanics. Can I show up how many of you have seen this equation before? Awesome, look at that. That is totally, so you guys see this equation. I think the day you discover that this equation is actually telling you what goes in must come out is the day you become a chemical engineer, okay? And, you know, so that's all it is. Del dot V equals 0 at steady state if you have no accumulation. So how is this equation modified when you have ionic current? Does it stay the same? Is it different? And so in this fine paper that I wrote after, with John after COVID, we derived the equation for this del dot of V0. Okay, it has some terms, it actually is. But the prefactor is the partial molar volume of the salt, which you can, if you think about thermodynamics, is never 0. So you add salt, the volume has to change, either up or down, usually up. Actually, usually down. Anyway, but it's always some complex function of concentration which we can measure. And so using that, we can then go to town. Okay? So now we have these, it's a complete set of equations. And we can determine concentration and solvent velocity as a function of space and time. Okay. What pops out of those equations, and that's shown in this paper for the first time, is that when you apply an electric field, there must be a cation velocity, an anion velocity, and a solvent velocity. The three things have to move. You cannot have a solvent being stationary. Okay. And these are very simple formulas based on that thing called the transference number that I will come to. Okay. So this particular expression I was very proud of when I saw that, because it's not there in the literature. It has been assumed to be 0, and it's far from 0, except if t plus 0 is 1, and that's a pathological case. So, so we set about, to measure this parameter called t plus 0 in our polymer electrolyte. And it turns out that the classical way of measuring it is this formula sort of gives that value. You have to measure a diffusion coefficient, you have to measure something called a current fraction, you have to measure the activity coefficient, you have to measure the conductivity. And by the time you make all these measurements and you're honest, you will get error bars that look terrible. Okay? And this is a plot that we proudly publish because we think it's the best measurement of transference in the literature. Okay? And when you do a best analysis of all of the data, what you get is the horrible realization that this number is negative in a broad range of concentrations to our best estimate. This is problematic. Okay? And here is one example of what the problem might look like. This is a paper from Münster, which is the leading, I would say this is the most well-funded battery operation in Europe. And in this paper, they give us top billing. They talk about different methods, and one of them is the one that I proposed. And they say basically that it's all wrong. Okay? This paper thinks the transference number is greater than 0.7, and that, in fact, we must be wrong. And it's a scathing. If you want to see a scathing paper, this is the way to write a scathing paper. Okay, it's a wonderful example. But there are others who took us more seriously. Okay? Here's a paper came out of MIT from Jeff Grossman's group, where they said they developed a new way of doing molecular simulations. That paper, by the way, just said they ignored the fact that we had derived things. They didn't say that this is the flaw in the derivation. They just said we were wrong and we don't care. This paper says that we have developed new techniques to measure the transference number, and that experimental results, which were ours, reporting negative cation transference, are confirmed. Okay. So there's debate in the literature, what is right, what is wrong. And the answer that they gave for this negative transference number is that when you look at clusters and you go and analyze your simulations, majority of the clusters are negative. So this is a population. Again, you're used to seeing dark colors means high probability. And this is n minus the number of negative ions in the cluster. This is positive ions in the cluster. And you can see it's all skewed above this line. And so this is actually the classical picture of negative transference numbers dating back to 1900s. Okay? That when you have structures, structures like this, if one positive ion is connected to two negative ions, and if this is the highly mobile species, then even though there are ions going in this direction, the net flux could be in the opposite direction. There is no thermodynamic violation of both charges going to the same electrode at t equals 0. It can't go on forever, but at t equals 0, you can certainly have that. And that's what, and that has also been known for many years, for a century. Okay? So this picture was intriguing. So what we did was we leaned on a technique that had been developed several years ago in this beautiful paper by Tom Zawadinsky and H. Halls, which said that you can determine transference numbers by NMR. In this NMR tube, you put 2 electrodes, in this case platinum. You apply electric fields and magnetic fields. You do an NMR experiment, like a PFG NMR experiment. But what you do is you measure, as a function of the applied field, the velocities of species. And now I'm giving you the exact definition of the cation transference number. It's the fraction of current carried by the cation relative to the solvent velocity in an electrolyte of uniform concentration. Okay? It's a mouthful. Oftentimes, I would also say that in the field of electrochemical transport, transference numbers are the most poorly understood parameter. Okay? Current, we know how to write. Okay? Current, I, is Faraday's constant times the velocity times concentration. You do the units, you'll get that right. So I plus and I minus are given. So if you want the ratio, you would say take I plus divided by I plus plus I minus. Okay? But what our stalwarts did was they said all the velocities, you can't talk about a velocity without a reference frame. You know that from Physics 101. And the question that people often forget is what is the implied reference frame from which these velocities are measured? And what the pioneers did was they said, use the solvent velocity. Okay. So in fact, the currents are all defined in terms of the solvent velocity as a reference frame. So when you apply a field, all things must move, and you want to sit on the solvent. For example, this is really important, right? I mean, you have a Tesla going, you don't want to stand on the ground and start measuring ion velocity. It has nothing to do, right? Because you get the speed of the car. So the reference frame is really, really important. And so repeating that definition and noting that C plus is equal to C minus, I get that the transference number is now given by this ratio of velocities. And because NMR is such a beautiful experiment, the error bars come way down. Okay? And then these are the measurements of the velocities in microns per second. As a function of salt concentration, you can see the R on the top. In the same solvent, but in a solvent called tetraglime, which is a PEO chain with 4 repeat units. And that's just because it's hard to stuff PEO in the NMR tube without breaking it. Okay? So we use an analog to get our results accurate. And this is the data. The orange symbols are the NMR measurements. I'm not belaboring the molecular dynamics simulations, but it's pretty nice agreement. And you can see that it has an odd shape. It sort of starts out at 0.4. It goes down to something like 0 and then comes up. Not very different from that PEO horrible thing that we had published based on that the standard way of looking at things. And because this has 4 oxygens and you need 6 oxygens to have a solvation shell, you drag 2 of these chains along with us. So you can, in fact, even rationalize the difference between this minimum being at one value of R, 0.16, and this at 0.08 because of that effect. And so under an electric field, this ion is dragging 5 or 6 EO segments. And in fact, when you do the same analysis that was described by the MIT group, and do the analysis, what you find is that the MIT group defined the cluster, but they didn't worry about how many solvent molecules were in each cluster. And if you take that into account, that dominates transference in our case. Okay. So, and that is the bottom line. That this tells you how, this color tells you how much solvent is there in each of these clusters. And in fact, when you do the analysis that is shown here, that is the important thing. It's these are the clusters are definitely skewed towards the negative side, but it's the solvent that dominates. And finally, I just want to show you some experiments done by my student Emily at a synchrotron where this solvent motion is measured directly. Okay. So this is the setup. This is a cell with an electrode on this side and that side. And what you do is you translate the cell in the X-ray beam and just look at the transmission. If the cell is uniform concentration, then the transmission is uniform, and the picture you get is flat. And let's see if that happens. You'll see this is so it's flat at t equals 0, and then as you polarize the cell, you get concentration growth at one end and concentration decay at the other end. So this concentration, which was initially something like 0.2, if I remember correctly, you get 0.35 on one side and 0.1 on the other side. And so this, of all the things I've shown you, and I've talked about concentration gradients, this is the first direct measurement of concentration gradient in exactly the cell that I was talking about. Okay. And there is no adjustable parameters. It turns out that the extinction coefficient of fluorine, lithium, et cetera, are all tabulated. So you just go, you measure the extinction, and you get out the concentration. If you know the concentration of salt, and you know the partial molar volumes, which we do, then you know the concentration of the solvent. Just basically 1 minus the C. And I was telling Emily, we should be able to get solvent velocity from this measurement. But how, I didn't. And then she came up with this crazy idea that, you see, this is an equation that is basically a solvent conservation, right? And the solvent accumulating in the little control volume has to be carried in, and because it's one-dimensional, it's in the x direction by the velocity. And so if I know C0 as a function of x and time, I get solvent velocity as a function of x and time. And so taking those data I showed you in the previous slide, and this is at the middle of the middle of the cell. This is the salt concentration at one point, changing as a function of time. We fit it to some curve. This gives us d0 dt, and then we also know what C0 is as a function of t. So from that analysis, we can get the solvent velocity as a function of space. Initially, it's minus 0.45 nanometers per second, and that's the V0 that we need to put into the transference number. With time, this solvent velocity goes down, and it eventually goes to 0, because at steady state, the solvent cannot participate. It can't go anywhere. Okay. And so, to my knowledge, this is the first time the solvent velocity has actually been measured more or less directly, because you can't argue about that equation. The last thing I want to say is that when you have a concentration gradient, you must have a potential gradient. And so, in the simplest case, you can just put Nernst's equation and take the logarithm of that and say that's the potential. So I'm imagining that you put a voltmeter with the negative electrode, and you have a lot of these electrodes in the electrolyte, and the question is, how is the voltage changing as a function of position? So, I'm assuming lithium to lithium, the same electrodes that I have same electrode reactions that I talked about. And if you know the concentration as a function of space and time, then conductivity as a function of space is known, and the transference is known, the activity coefficient is known. The overall potential has two terms, and what we call an ohmic term and a concentration polarization term. Okay. The ohmic term roughly tells you what is the conductivity contribution to the voltage. And that ohmic term is shown in this middle panel, and you see initially it's about something like 0.25, and at final time it's about 0.35. this concentration polarization is much larger, 0.25 versus 0.025. Those of you who stir milk into your tea, it's like asking, what is the energy I need now to take the milk out, right? It's huge, impossibly huge. The bottom line is that the potential needed to drive these concentration gradients is so great that the conductivity doesn't matter. So improving conductivity is in fact completely pointless. The conductivity of ppm is 50% of PEO, and yet it supports twice the current. It's because of the fact that these other quantities, the activity coefficient and the transference, are more favorable. So I want to finish by talking about all solid batteries. It's a very hot topic. If you Google it or AI it, you will find lots of interest. In the end, I started with this, and one approach is to use solid electrolytes. And this is a paper that changed the field. Okay, in 2012, Kano, who's a very, very amazing scientist in Japan, published this paper on a lithium superionic conductor. No hype, completely reproducible, beautiful work. Right? He showed a plot of conductivity versus temperature. He has a whole bunch of electrolytes, including this new electrolyte that the lithium germanium phosphorus sulfur electrolyte, which has this conductivity curve. You can see it's higher than everything. This is the electrolyte that you carry in your pockets. And so the conductivity that you get is actually identical to the liquid electrolyte. And at low temperatures, it's even better. The poor polymer electrolyte that I've been talking about are all here. Okay? And so there's a natural question. If you want to study solids, would you study this lousy one or that amazing one, right? And most people would choose an amazing one. I would argue, why choose the amazing one? It's already done. There's no headroom. There's not much motivation to make it better. This one has lots of headroom, and I also showed you that conductivity is not the right parameter. So that's the other flaw with this thinking. So there are many announcements of all solid batteries that quickly disappear. Okay? So in 2022, Toyota announced that by 2025, their first hybrid vehicles would have a new battery. Okay. As far as I know, nobody has bought a car worldwide so far that has this battery that they talk about. It's very hard. Okay. There are companies like Solid Power. If you have money to invest, you can invest in this general idea of a solid battery. Solid Power is one publicly traded company. In my view, these, lithium germanium, they are like it's like a flower pot. It's like a ceramic, right? Like a dinner plate. Let's say you start out, and I'm showing here one set of particles in the anode that contains the lithium and a cathode that doesn't contain the lithium. And now you want to move the lithium from there to here. These particles will shrink. Even a 1 nanometer shrinkage makes this battery stop, right? It's an insulator now. So this battery would stop working at this stage. In my view, there is no way a ceramic can ever function in a battery that contains particulate electrodes. They have to have compliance, right? The beauty of liquids is that they're infinitely compliant. Polymers are partially compliant and have a chance. I'm not sure that they will, but in the end, the compliance of the solid electrolyte is really, really important for studying batteries. And I would argue that until some polymer scientist is involved with the development of solid-state batteries, these batteries will never be in your hands. That's my prediction. So I want to conclude. The molecular arrangements around ions in different solvents are very similar. Actually, 6 water molecules solvate cations as well. But the time scales can vary by orders of magnitude. for reasons that are not totally obvious. Neutral solvent molecules must move when current flows through an electrolyte. This is, I derived a continuity equation, I derived a simple velocity expression for the velocity. And the movement of neutral molecules, which was the title of my talk, is not some academic little sidebar. It is the design principle on which we found ppm relative to PEO. The difference is not anything except the movement of the solvent. And I think as bad as polymers electrolytes are, they offer the only approach for allowing the battery to breathe. Okay. So with that, I want to acknowledge the contributions of many group members that I went through my talk. Xiaopeng Yu is a synthetic chemist who made the first ppm polymer in my lab, and yeah, I've talked about all of these folks. I also say that my journey began in IIT Kanpur, so for all you students, that's a picture in 1978 in the hostel that I was in. This is a picture some years later of the same friends at the college reunion, and that some of you know a professor we know that we affectionately call Gandhiji, K.S. Gandhi, and this picture that I've shown often was taken from my notes on fluid mechanics. Thank you.
Thank you so much for a very stimulating talk. We open the floor for questions. We will have roughly 15 minutes. And I would request that perhaps stating your name and affiliation might help when you ask the question.
So, when you have a big polymer molecules with lots of solvations shell, that will get dragged around along with the ions, and that will give rise to a velocity.
Yes.
However, if you take a smaller one, which then it will be the probability of dissociation will increase, and because of that, the velocity would be more, which is what you have attributed by saying that now instead of one PEO, there are two ppm are interacting. So if you take it extreme and you further decrease it, then again you would see the same behavior and have a more transference number. Does that make sense?
So, so the transference number is a transport parameter. Normally, it is interpreted as the fraction of current, fraction of V plus divided by V plus plus V minus. The point I'm making is that when you, so the objective always is to move the cation and nothing else. That's the perfect electrolyte. All the other velocities are 0, you'll get 1. The point I'm making here is that regardless of whether you move the solvent or you move the anion, if you get 1/3 for this ratio, the electrolyte will be the same. Okay? And it depends on how you change V0 and V minus. That tells you what the final answer is. But in the end, the individual contributions are not relevant for continuum transport.
Hello sir, this is Bhavya Bhargav, a PhD student working with Professor Rajiv Bandyopadhyay, Chemical Department. I wanted to know what are the sizes of the polymer molecules that you are using?
Yeah, about 30,000 grams per mole. At that, above 5,000 grams per mole, molecular weight.
1 kg per mole.
What?
I mean 13,000 grams per mole, 13 kg per mole, right?
Yeah.
So, I mean, so the size of a molecule of this polymer would be typically in near 1 micron?
No, 30 is like 7 nanometers, 10 nanometers, the radius of gyration.
Okay. So, let's say if the effect of transferase number that you showed, that multiple ions were actually, you have a cation and anions, they are bounded, and the even though the thermodynamics of, because of the gradient of electric field is causing net effect changes same, but they are two anions are carrying one cation together. There was one picture.
Yeah, yeah.
So if you have there is solvent motion is also happening because of these movements, right?
Right.
And people don't account for that.
Right.
So if the sizes of these polymers, or let's say new fields, I'm trying to understand how this knowledge can be applied to other fields. For example, if you have other type of gradients or other fields, and you want to apply the same knowledge, because people don't, even I also don't take account for the if I have stagnant motion or my experiment is stagnant, we don't account for fluid velocity. And
so this was, sometimes the velocity that I've noted is often called convection. And there's no convection here. It's just that, so I think it's more subtle than convection. And the big difference between a normal system and electrochemical systems is electroneutrality. If you have, let's say, two species moving through a polymer and you want to select one species, they would not be bound by electroneutrality, they would be bound by Gibbs-Duhem equations. And so the physics would be different, but even in that case, let's say you have glycerol and water and you want to get glycerol, the solvent motion has to be accounted for, and it's only in the dilute limit that it's not accounted for. So,
okay. Yeah. And if the size of whatever we are accounting, if it increases, the effect on the solvent might increase? I mean, effect of solvent motion might increase, you might think?
No, so in polymer science, and there are many here, the assumption is that in solvents you'll get a lot of motion, because solvents are fluid and polymers are thick, goopy stuff, they shouldn't move. It's exactly the opposite in electrochemistry.
Okay.
Because the solvent, the solvation shell is more or less the same, but the chain, a lot of segments are connected. So there's a lot more dragging in a polymer than a small solvent. So in fact, all our intuition in polymer science had to be thrown out the window when we thought about these.
Okay, thank you, sir.
In terms of electrochemistry, I can talk about it. But transference number you are talking about, I didn't see you are not talking much about anion dynamics. You are only concentrated on lithium dynamics. So what is happening? Because polymer is lag behind, lithium is going out, but what anion is doing is going together?
So in our simulations, which I didn't describe in detail, but it's in our papers, we certainly account for anion dynamics. You have to account for it. And roughly spoken, the answer is this, right? Because of electric fields and mobilities, the cation moves in one direction and has a certain volume. The anion moves in the separate direction, it has a totally different volume. And the solvent has to fill the gap. That's continuity, roughly. So those formal equations that look a little imposing is a way to account for that. And prior to our work, everyone just focused on the cation and anion, and then made up stories about how it stays, that picture that I showed you is completely made up to account for the fact that the whole electrolyte can't move. Okay. So, and I think that is all of the problems arise because of, the microscopic problem. So I think that you're exactly right. If we didn't do justice to the anion work, but we did, and I didn't belabor it because I don't want to keep you longer.
I didn't see that, so maybe I can look at it. So another, maybe small, if there is no other.
Yeah.
One thing is your PPM, you are saying this is one of the best, but PO is well known to be one of the ideal candidate.
Yeah.
So PPM, you are saying that, but your 2 chain is required to solve it 1.
Yeah.
The coordination sites are very less in PPM.
Right.
So that means you are less amount of salt you are dissolving.
Right. That's actually good.
That is good in terms of maybe polymer science.
Yeah.
But in electrochemistry, do you think that is good?
Absolutely.
Because you are talking to dilute solution.
No, this is not. This is far from dilute solution. It's in fact all concentrated solution theory. So, so here's the point, right? First of all, my argument is that for any electrolyte, you should look at the limiting current, not the conductivity.
Yeah, that is one point. I agree with you.
Okay, you get that?
Yeah.
And the limiting current is governed by 4 parameters. Okay, that's the conductivity. I told you it's half of PEO. If you just looked at that, you would throw that polymer out and not do any experiment.
Because if you have a less salt, maybe the ion aggregation is
No,
less.
it's not. It's at the same salt concentration, it's half. But at R of 0.1, see, PEO for a certain thickness will never support the current that PPM supports. And the optimum salt concentration that you should use in a battery is the peak of this plot. And because it carries more charge. And that's actually a big plus for the PPM. It also, I mean, whether PPM or I'm not worried that much about this. The point is that the design principle is a little different if you just look at conductivity. And that's the point I'm trying to make. There are many, many other terms. For example, this open circuit potential has a lot to do with activity coefficients. And because PEO solvates the ion so well, the activity coefficients are through the roof. Because strong interactions means high activity coefficient. And so it's in fact the activity coefficient that is important. And when you have 4 parameters and they're all changing in some way, it's tough to sort of say which, what matters and what doesn't matter. And I am being a little simplistic in saying conductivity doesn't matter. What I should say is that polymer electrolytes are so lousy that doubling the conductivity will have no impact.
No impact, yes.
That's what, if of course the electrolytes you use are 10 times better, and there 1 over kappa is significant relative to the other term. But in polymer electrolytes, we have to worry about the other terms first. If we can improve kappa, it will be good at some point, but we are at least a factor of 5 away from that.
Thank you. We can discuss.
Yeah.
Hi, sir. I am Mohit, student from the MEMS department, Material Science. I had a question from the formula you had given regarding the concentration gradient. So how much does it match with the experimental results? And can the same formula be applied for solid-state batteries?
The classical solid-state batteries?
Yes, sir.
Okay. Yes, I have not, in various papers, we have shown how the concentration gradients match what we expect. Okay, because we have already published the transference number, we've already published the diffusion coefficient, and the match is not perfect, but certainly not bad. Okay, and within the error bars that we have published. In a classical solid electrolyte, the anion framework is static. So the negative concentration is uniform, which means that in the absence of any defects, like I'm thinking of a classic solid, there can be no concentration gradients because of charge neutrality. So what happens in a classical solid electrolyte is one lithium comes in, at the same time one has to leave from the other side. Okay? And so that is the difference. In a classical solid electrolyte, conductivity is the only thing that matters. And it's funny that there are 2 competing types of solids. In one case, the conductivity is the only thing that matters. In the other case, it's the other things that matter. But that's the answer. By the way, thank you all for sticking around. It's kind of, yeah. Yes.
Wonderful talk, Nitash. Slide 55, you had a continuity equation, which you said, slide 55,
Yeah.
partial of C naught is
Yeah.
equal to minus of partial of x of C naught
Yeah.
A. There's no diffusive term there. I would have expected a diffusive term because you have gradients in the solvent molecules. Why don't we have that there?
because this is mass balance.
Right.
And it's implied, the diffusive term tells you what C0 will be as a function of time. But if you use this equation, it cancels out. It doesn't matter. So if I want to predict these profiles, I have to get a diffusive term. But if I want the solvent, this is just mass balance, right? The solvent accumulating in my control volume, and it's a one-dimensional thing, must be equal to what solvent comes in from one side and what leaves from the other side.
But remember, this is a continuum model. It's not at a... Right?
It's continuum.
So when you write the continuum model, you would have a convective term, which is what you have written, plus a diffusive, because your molecules are diffusing over the average.
I'm going to the first, that's what you get at the second stage of mass transport. This is at the continuity equation level. This is dc dt, d rho dt plus grad dot v equals 0. That's mass balance. And this is the mass balance for the solvent. So you're exactly right. In order to fully solve the problem, you need the diffusion coefficient, and in fact, that's the nature of the question, that when you look at, I'm looking at one aspect of the data, right? I'm just looking at concentration as a function of time. But if I wanted to really understand, when I go into, in fact, I also need the transference number.
Yeah, because C naught is the concentration of the liquid, of the solvent
of
molecules.
The solvent.
But then you also have the positive ions and the negative ions.
Yeah.
So it's not the total mass, it's just the mass of...
The mass of the solvent accumulating
must
be equal to the mass coming in on the left minus the mass going out on the right.
Okay, so maybe, okay. That's about it. Thank you.
I thought there was one last question. Okay.
Hello sir, I am Vidya Jadhav. I am PhD student in Chemical Engineering Department. So my question is that can we use ferromagnetic fluids and we can apply, or can we apply magnetic field to transport the ions? It's just
first of all, I know very little, and I know even less about magnetic fields. So I don't know if ionic motion can be coupled to magnetic fields. I suspect it's not a good direction to go. Keep in mind that the electrolyte has to block all electrons. It can't have electronic transport. And so that usually rules out the magnetic part of the Maxwell's equations. And so I don't think that even simple ferromagnets and things have too much electronic transport, I think, to be directly applicable. And there is some people in the literature who sort of have suggested that. I ignore them. But that's only because I have limited time, not because it's actually worth neglecting. But anyway, that would be my unvarnished input.
Thank you, sir.
Okay, so at this point, let's thank the speaker again for all the engaging discussion. So next, may I request our head, Professor Mahesh Tirumkudlu, to kindly come forward and present a memento to Professor Balsara as a token of our appreciation.
Wonderful. Thank you. Oh. Thanks for your question.
So we are at the end of the talk. On behalf of the Institute Colloquium Committee, as well as Department of Chemical Engineering, we would like to sincerely thank Professor Balsara for sharing his time, insight, and then inspiring work with us today. Again, at this point, I would like to thank Professor Chandra for facilitating this, Riya for arranging a lot of things, PRO office, CDEEP, our office staff as well for their support throughout the duration of his stay. Thank you all for being here at this evening. With this, let's conclude today's talk.